As we have talked about before, protons can sometimes decide that they want to change into a neutron, and vice versa. This happens in radioactive decay and will change the atomic number. In alpha radiation, 2 protons and 2 neutrons, sometimes known as a helium nucleus, is emitted from a main nucleus. This drops the atomic number by 2 and the mass by 4, but beta radiation is far more complex. Beta radiation can happen in 2 ways. The first way is when a neutron collapses into a proton. As the neutron is slightly heavier and has no charge, the extra mass and a little bit of negative charge is released in the form of an electron, which is a beta particle. But it gets more complicated as quantum theory likes to get involved. Quantum theory states that it's not only the mass and charge that must be conserved, but also momentum and spin must be conserved. For this to be fulfilled, there must be a third particle in play. As we know, the momentum is mass times velocity. Spin is far more complex, and I'm going to save it for the video on the standard model. But for now, the facts that you need to know is that an electron has a spin of 1/2, as does a neutrino. The other way for beta radiation to happen is a proton forms into a neutron. However, this time it releases a positron and a neutrino. A positron is the antimatter equivalent of an electron. In fact, in the first example, the extra bit of mass that comes out is an antineutrino, just a little bit of antimatter. Electron is the most well known of the major group of particles known as the leptons. Now, there are 6 flavors of leptons. In physics, flavor doesn't mean what it tastes like, it's more like a species of particle. So all the different leptons have similar features which make them leptons. They differ in very slight ways, the main one being the mass. These flavors of leptons can be split into generations. Each generation is more massive than the one before, and with greater size comes greater instability. This is why we knew loads about electrons, because they were one of the 2 most stable leptons. Now it is known that neutrinos existed, but it wasn't until the neutrino oscillations were discovered that it was found that neutrinos could have flavors, which then meant that we could have different neutrinos. It was in 1962, Leon N. Lederman, Melvin Schwartz, and Jack Steinberg showed that there was more than one type of neutrino by detecting the interactions of a muon neutrino, but at that point it was actually called a neutretto. Personally, I think neutretto is better, but muon neutrino. This discovery earned them the 1988 Nobel Prize in Physics. With tau not being discovered till 1975, the discovery of the tau neutrino wasn't until 2000, although its existence was expected. So what are the 6 different flavors of the leptons? Well, unless you haven't been paying attention, then you should already know what they are. You have the 3 main leptons and then their neutrino counterparts. So there are the first generation leptons, which are the electron and the electron neutrino. Then you have the muon and the muon neutrino, and tau neutrino. The electron, muon and tau all have a charge of -1, while the 3 neutrinos have no charge. The neutrinos themselves are nearly massless particles proposed by Wolfgang Pauli in 1930 to account for the slight loss in energy momentum in the process of beta decay. Neutrinos have some interesting properties, mainly their speed. As they are almost massless, they travel near the speed of light, but some variants of quantum gravity will allow them to travel faster than the speed of light. It was originally measured as 1.00051 times the speed of light. Later on, it was then changed to somewhere between 0.9990976 to 1.000126 times the speed of light, somewhere in that gap. In September in 2011, the Oprah collaboration released calculations showing that neutrinos had exceeded the speed of light. And of course, this is a huge deal, something that travels faster than the speed of light with mass. So they repeated the experiment in November 2011 and calculated the individual velocities of neutrinos, and the results came out the same. However, in February 2012, it was found out that they had a loose wire on one of their atomic clocks. Between Icarus and CERN now, it has been decided that there is no discernible difference between the speed of light and the speed of neutrinos. They are basically the same. There is of course now many different sources of neutrinos. the nuclear reactor being the most obvious one for beta decay, but also all the way back to the Big Bang. Nuclear reactors are a major source of neutrinos, as during beta decay, about 4.5% of the total power output is radiated away via neutrinos, or technically antineutrinos. That's about 9 megaelectron volts for an average fission reaction, which releases 200 megaelectron volts. Obviously, if fission releases neutrinos, so does nuclear bombs. They produce a huge amount of neutrinos. In fact, they produce an insane amount of neutrinos. Fred Rines and Clyde Cowan actually thought about detecting neutrinos from nuclear bombs before using reactors, but thanks to J.M.B. Kellogg, they used fission reactors instead. Fission bombs, or the A-bomb, releases antineutrinos, but the fusion bomb, or H-bomb, releases both due to the fission reaction initiating a fusion reaction which initiates a fission reaction. Another source is known as geoneutrinos. These are neutrinos that have been naturally emitted by the Earth, usually from uranium-238 and thorium-232, but also a little bit from potassium-40. They are known as geoneutrinos as they provide valuable information about the Earth's interior, and they were first found by the Camland experiment in 2005. So the question that might be on your mind is, what do we use neutrinos for? I had the same thought, so for starters, we have done the first ever transmission using a beam of neutrinos in 2012 by US physicists. It may have been highly preliminary, as it only operates at less than 1 bit per second, so will obviously require lots of development before it can be used in anything useful. However, the work proves the concept that physicists have been thinking about for years, and that could be used in situations where other means of communications are not feasible. Electromagnetic radiation, which is what we use at the moment, is easily transmitted, easy to detect, and can carry a lot of information. But it does have some situations in which it doesn't work, for example in a nuclear submarine, which can remain submerged until they run out of food or water. However, seawater is opaque to electromagnetic radiation at the wavelength short enough to transmit useful information. Therefore, what we do is float a radio antenna to the surface to receive signals. This restricts their speed and makes them easier to detect, so for war games this is not a feasible solution. So if we were to use neutrinos for communication, this would solve this problem, as neutrinos can go straight through seawater. As a neutrino is only affected by the weak force and very slightly gravity, it can pass through almost everything without interaction, so oceans are not a problem for ghostly neutrinos. Just to give you an idea of what it takes to stop it, not even 1,000 light years of lead could stop a neutrino. And you thought gamma radiation was good, right? They even thought that they could use communication to faraway stars with neutrinos, to see if there's any life out there. However, all the neutrino-based systems come across the same problem. As it takes over 1,000 light years of lead to stop one, most neutrinos pass straight through a detector. To transmit information at a reasonable rate, you need an extremely intense neutrino source and a very large detector. The way we tested it is we encoded neutrinos with the word neutrino and used it to modulate the neutrino beam with a bit rate of 0.1 bits per second. The message was received with a bit error rate of 1%, which allowed the message to be decoded easily after one repetition. However, it's not viable at the moment. The short distances, the low data transmission rate, and the extreme technology required are somewhat holding it back. The machines weigh several tons just for reference, so it's not exactly going to fit in your pocket. So it might not seem like there are many benefits to having a neutrino-based system instead of light, but it actually shaves off valuable time. Radio waves must curve around the planet, and microwaves have to go into space and come back. Neutrino beam could just go through the Earth, making it much quicker than electromagnetic waves. Also, considering that their speed difference is so close, if not the same, this would save a lot of time. Considering they spend billions to put in wires across the Atlantic Ocean to connect London to New York for the stock exchange, I feel this could have some feasibility. Now for a little bit of history on neutrinos. In 1931, Pauli presented the hypothetical neutron particle. Notice how it was called a neutron to begin with. He is actually referring to a neutrino. Then in 1934, Fermi developed the theory of the weak interaction and baptized the neutrino. only because Fermi was Italian and added a little bit of an Italian twist to make it his own. After a while, in 1956, there was the first discovery of a neutrino via an experiment. 1962 was the first discovery of another type of neutrino at the Brookhaven National Lab. Then in 1968, there was the first successful experiment which detected electron neutrinos from the Sun. 10 years after, in 1978, there was the detection of the tau lepton, and the existence of the tau neutrino was theorized. In 1985, the IMB experiment and a Russian team's report that neutrinos have a non-zero mass. Then in 1987, we found a burst of neutrinos from a supernova. In 1991, the LEP Collider did experiments showing that there are only 3 light neutrinos. Then in 1998, we confirmed that neutrinos have mass. That is pretty much all I'm going to say about neutrinos at the moment. Make sure you watch the next 2 videos on quarks and then on the Standard Model, which will cover the bosons. Thanks very much for listening. Bye!